Ready to go. Now, so kind of where we left off. We're doing micro. A quick review for micro, and they sort of spell out the stuff on what you need to know. But this is sort of, to me, I'm going to try to highlight film micro over today and Friday, what I think are the relevant things from an MCAT perspective that are there. And when we were here last time, just a little bit about the anatomy of viruses first. And even though when I do micro, I don't talk a whole lot about bacteriophage, at the very least, you need to have some degree of familiarity with that. Like we said before, with things like lytic versus lysogenic, and particularly lysogenic conversion. And then we're also looking at the genetic aspect, which will be things like conjugation, transformation, transduction, that, those aspects are also going to be important to be able to remember. And then certainly, the basis of bacteria, the gram-positive v gram-negative distinctions, all that stuff. I mean, I think the anatomy portion is fairly straightforward. We're dealing with eukaryotes versus prokaryotes. But I mean, I think when we're looking at gram-positive versus gram-negative, I think that's really a critical piece. So let me do the viruses, since I started with that first. So I don't know if you use this text or not. Did Dr. Maurer use the Nestor text when he did micro, or did he use something else?
He had it on, what was it, Pearson Plus or whatever it's called. So it would be like Mastery, I think.
Yeah, I mean, I too technological for me.
Yeah, I don't know exactly what it's called.
I don't know what he's. We changed tests, but I'm going to use the Nestor text because I'm most familiar with that, and I'm just going to buzz through this, and I will put this on. This is already on, and the 8 is on, but I don't think the chapter 3 is on. So you'll be able to review these when I put them on the blackboard. And then I've got to do something with these YouTube presentations. For whatever reason, I'm trying to convert these to YouTube, but I didn't make them. Students having trouble visualizing because I made them private because I was afraid of copyright infringements. But apparently, Dr. Buxton tells me that I don't have to worry about that. That YouTube tests and checks for that, so I got to read it. Dude, I hate that. Work. I could be watching sporting events instead. So, background virus means poison. Viruses. So the distinction here, very simply, bacteriophage infects prokaryotes. Their relevance is important. I know one of the passages we do here on our, some of the tests that we construct here, but the usefulness of bacteriophage as an alternative source of antibiotics is something that's coming, because antibiotics are a big problem. I've been around since the early days of when we started to see, but prior to the onset of MRSA, to give you some idea of how long we've been dealing with these problems. So the alternative nature of that, size, not so much, but then these basics you certainly need to understand. And again, the distinction between what the capsomeres are, which are the subunits, and their configurations. So their configurations, when you see this geometric configuration, we call them isometric as a nickname because all the sides are the same, because it's a bunch of equilateral triangles. Technically, it's an icosahedron, the analogy I used, that 20-sided game die. And the distinction here, so the nucleocapsid just has to do with the genetic material, which of course DNA or RNA, never both. And then the distinction between the enveloped virus and the non-enveloped viruses. And again, typically, how are non-enveloped viruses or naked viruses? They typically come from the host cell lysing and sort of exploding out when they reach something that is typically referred to as the burst size. And that's why they can replicate so rapidly. Rather than having, the bacterial growth of binary fission, 2 to the power, 2, 4, 8, 16, all that 2 to the power table. This is, you could have a 500 or 1,000, let's say, burst, and they could infect 1,000 more cells. And so now you go from 1,000 to 1,000,000, et cetera, if you want to look at that, like, depending on what the burst size is, to power whatever the growth cycle is. And that's why some of these viruses are so devastating in a short period of time. So Ebola would be, although Ebola doesn't necessarily use burst site or COVID, but their replication is almost continuous in nature. Those two, for example, are in this category of enveloped viruses. And the distinction with the enveloped viruses is they exit by either budding or shedding, that they pick up a small portion of the envelope. So during their replicative cycle, what they do, they replicate capsid proteins, they replicate how they attach by way of the protein spikes, and they replicate whatever associated proteins might be in the package, like RNA reverse transcriptase for HIV, for instance, or protease for some of those, for instance. And what happens is that in the naked virus, they're just assembled and they explode out. In the enveloped virus, the protein spikes are embedded into the envelope. And the good news and the bad news. The good news is that the envelope is now a target for antiseptics and disinfectants, and something that we can target, and why they are easier to destroy environmentally than the naked ones. That's certainly a significant portion that's there. I'm not very good, and it's in that handout that's on the blackboard between positive and negative sense strains. I think Dr. Hillwood would be handy in that, and I will ask her. She can either brief you or brief me so I can brief you on the idea of positive and negative sense strains. Because that's more of a cell molec type of thing than something for me. Because I'm not a smart machine, not even close. Is any of it? I told you, I'm the good test taker, not the smart guy. And I don't get, the genomes are interesting in that regard. And so we see both double and single stranded, which is rare because you don't see that much single stranded DNA or double stranded RNA. That's where the unique portion of viruses are. And depending on the configuration, that determines the shape, the architecture, whether you're going to have something that's going to be encased in that icosahedral or what they call helical or filamentous. So that sort of dictates how that capsid, the filamentous or helical, the capsid kind of goes round and round, the way you would put tape on a hockey stick, the way that particular assembly goes on. And the oddball are the complex ones. And we have a few that are complex that affect us. Influenza, parainfluenza, which is RSV, are in the complex category. And those oddball looking ones you see for the complex viruses, the bacteriophage, are almost all in that category, being complex viruses, so they're really odd. And that's that tail fibers and spikes, and they're very, very significant with regard to, the spikes really dictate what they can attach to, and they give you a nice synopsis. So this, typical adenovirus, which is more or less a cold virus, more so than anything else. Tobacco mosaic, probably the most studied virus, because it affected the tobacco crop, which is the biggest cash crop ever, for a very, very long period of time. And then these variety of bacteriophage viruses. Broad brush. I don't think you have to know this. Broad brush, DNA viruses, if there's a watchword, latent. DNA viruses, the host cells frequently incorporate the DNA, particularly for herpes and HPV. So once you got them, you got them. Whether they were going to affect you again is a different story. But if you got a wart as a kid, there's always a chance you can get a wart. If you were exposed to, sexually transmitted HPV, it may only affect you one time, or it could come out at any time. That's just the nature of it. And again, the nature of them being latent viruses, and there's any number of factors that, that facilitate the reactivation of latent viruses, and very much so. And if anything, the poster child for those are herpes viruses. So if the herpes viruses, particularly VZV, varicella zoster virus, we call it chickenpox shingles virus. So effectively, we all have been exposed to that in one way, shape, or form. Whether you had it as a kid, like I did or my kids did, or whether you're immunized like many of you were. Because the immunization started around 1995, and that particular immunization came out. So my kids all had it. And interestingly, presented differently in all three of my non-biological siblings. Okay, one normal, one minor, and my daughter was nearly life-flighted to Children's, all with chickenpox, all within 2 weeks of her. So that's the big nugget there. Pox viruses are large. Herpes, there's about 6 or 7 different variations. So 1 and 2, herpes 1, oral herpes, most common, about 90% of us have been exposed to that by now. Herpes type 2, much more frequently associated with genital-based herpes. These days, and we just saw it with Michael Douglas, and I think we saw it with Martina Navratilova, the tennis player. They're getting a lot of oral carcinomas that are herpes-based. So they're genital herpes or genital HPV because of oral sex. Come here, and there's nothing unusual about that. No, it's not a big deal. But I'm just saying we're seeing an uptick in that. That's with regard to that. So herpes viruses, which are a little bit larger. Noteworthy, HHV6 has an association immunologically, at least probably not a cause and effect, but there seems to be a correlation coefficient that's being studied with MS. And HHV8 certainly is associated with Kaposi sarcoma. So these latent ones, those are another big deal, is which ones are associated with cancer. The herpes family, HHV8 with which is Kaposi's, which is we see with HIV and immunodeficiency, though not exclusively with that disease. Kaposi described that in the late 1800s to give you an idea. And as far as we know, HIV is a hybrid virus that came about most likely from failed attempts in what were tragically called laboratories, and I've seen videos of this, in Africa to make polio. So they're trying to make polio vaccine in such squalor, such horrible condition with diseased monkeys, that they ended up creating this oddball virus that eventually has become, that mutates, it's the worst of both worlds because DNA viruses are latent. RNA viruses mutate. COVID mutates. Okay. We're probably seeing that a little bit now with RSV mutating, because before it never used to affect the elderly. That's what put my mother-in-law really in the hospital. It created a significant downturn with her, who was more or less independent prior to that. I only see my wife like once a week. It just bothers me. But I am watching a lot of sports. Okay. What are you doing? Oh, I'll keep busy. Here's a game. And certainly the poster child for that is influenza. So those are all RNA viruses. Not all of them mutate, but they do, because we don't have the proofreading capability in our cells comparatively. And you probably should have a quick look-see at antigenic shift and drift. So that's part of it as well, because that's sort of the genetic variations there. Let's see. Noteworthy. So here, when you get this next one. So here's, when you look at coronavirus, and you can see by the age of this, they don't even mention MERS or SARS, which were both variations, in which we saw some of the MERS rear its ugly head at the World Cup, by the way. Okay, so there was some respiratory stuff going around that was non-COVID, but COVID-like. And then, so they all came from this. And what happens is the spikes, because of genetic variations on the inside, the spikes begin to vary, and that's where we see all these variations. And it's going to be continuous that are there. These are the flavivirus. Rhabdo is one that was well studied. That's rabies. Phyllo is Ebola. That's well studied, but most of those are either transmitted. That's a variety of different types of transmission. And these two, the orthomyxos and the paramyxos, this is where the RSV is. This is where the influenza is. They're oddballs. I think that's basically everything. And the other one that certainly you should be familiar with, because it's always going to be a buzzword for now, is down here is the retrovirus, which I always refer to those as the worst of both worlds, because you have the latency as it incorporates in your white blood cells. It targets the helper T cell, the single most important cell in your immune system. And it unfortunately, so it has that DNA-like ability to develop almost a type of latency for some years, particularly if it's untreated. It appears to be latent, and then it progressively increases. And what makes it so difficult and why you have to use multiple antivirals to treat it is it mutates, because there's so much, because its initial stage is RNA being rewritten as DNA, and there's absolutely no proofreading. So you end up with combinations of that. Name's not terribly important. Be familiar, if you can, with major viruses, how their transmission is. Generally accepted 4 routes. Okay, enteric, fecal to oral, because most of the time, if it's spread that way, those are the systems that it affects. There are some oddballs. Polio. It's fecal to oral, but polio, however, although it enters through the GI mucosa, affects the nervous system. So that's an oddball with regard to that. Respiratory, for the most part, ones we're most familiar with. A lot of these are not, this is the way I would phrase it, these are the most common routes, but not necessarily the only route. So again, for this, zoonotic, typically brought to you by another member of the animal kingdom, would be the way it was described. The subcategory is arbo for arthropod-borne insects, things like that. So that's really our good old phylum Arthropoda, that type of stuff, versus ones that are direct. And you can get rabies, you can get rabies from a person if they bite you, if you didn't know that. And that you can have direct transmission. It's in saliva. It's where that comes from. And it happened to a neighbor of my in-laws, my first set of in-laws, way back when. She worked in where Children's is now. That used to be the old St. Francis Hospital. That had a drug and alcohol detox unit, and also had a big psych unit. It's a very, very large building. She was a psych nurse. She got bitten by a guy who was crazy, had rabies. Just saying. This is the bacteriophage. They either will be lytic. Productive means they're actively producing the virus. It's a little bit different, like having a productive cough with mucus. So they either lyse and the host cell dies, or they become a lysogen, which means they're basically a plant for making and expelling more viruses. And then they can go from that latent state and we can actually convert them into the lytic stage. And they go through all these steps. Again, the steps are important, and the big difference, because this is how you address them when we get to human viruses, is in between the entry and the synthesis. In humans, we have that uncoating, which was the earliest kinds of antivirals were uncoating agent to use for influenza. They weren't very effective. I don't know if they're still using them. That were there. And you probably have seen this, and I don't know how important it is to look at it, but I think the nuance, again, is that the entire virus does not enter, but merely that whole assembly, that complex assembly, is really, to me, a sophisticated syringe to inject the DNA, more than anything else, the way I would describe it. And then that burst size is how many it is, so you get 200 popping at a time, and the next set of cells and 200 more, etc. Temperate phages are ones that become incorporated, and so the infected cell is now called the lysogen. Yes, it can convert to being lytic, but the big thing, you say, when you have this integrase inserted at a specific site, they use the term prophage for this, and let's say for HIV, it's called provirus. That's another one of the areas with HIV that they've started. It's called integrase. So so now they're doing antivirals that combat its ability to integrate. And so they have they're constantly being studied for things like that. And so effectively, what happens is if you can interrupt any of these phases, that are there. And then the phage induction is to be able to induce it to become lytic. And then this is the big thing with lysogenic conversion or true superinfection. Okay, changing the phenotype, encoding toxins. So the diphtheria toxin, botulism, Shiga toxin is very famous. That when you hear a lot of people dying from food infections, like the nasty kind of E. coli, this O157H7. You guys know what the O's and H's relate to? Okay, we'll look at that at the gram negatives. The O-specific antigen or polysaccharide is that chain that comes off a gram negative. It's used for identification. The H antigen is a flagellar antigen. And that's how you, when they examine E. coli, how you can tell which strain it is that might be causing. And the worst is that O157H7. Because it typically has that. And there's about 5 or 6 other species that have it. Just saying. Salmonella, okay, like that. I was in intensive care with salmonella back in 2006. I didn't tell you that anecdote?
You got it from a salad or something?
Yeah, I got it
yeah,
from Panera's.
Panera. Oh yeah.
Because and eventually that guy was in Butler, but he was like in fruit, lettuce and tomato that was contaminated, and they found some sheets and things like that. That was a Panera sandwich. Unbelievable. I mean, I told you they called my 87-year-old mom at the time when she was alive, telling her I was close. That's scary. So all of those things are part of it. And I don't know about the filamentous and things like that. I think it's a little bit transduction. To understand the concept of transduction, to simplify it, bacteriophage or acting as a vector, just a conveyance. So what the bacteriophage is doing is it's taking a genetic particle from one bacteria and facilitating its non-contact transfer to another bacteria. The same thing is conjugation. You'll see, and I'll show you those slides just to review them with you. Okay? The only one that involves direct bacteria to bacteria contact is conjugation. Okay? It's so terribly, because those are definitely areas to look at on this test. So to me, the most simplistic way to look at it, that bacteriophage is really not a bacteriophage infection because it's not carrying viral DNA or RNA, viral genetic material. It's carrying, it's just a conveyance for bacteria. It's an oddball that happens every so often. But obviously, so often enough, that can alter things that are there. And I don't think they get too much into distinction between specialized and generalized and how it's recombinant, though you can look through that. Preventative things. The restriction and modification syndrome, the restriction enzymes are what's used for genetic engineering. The modification, it's really to me like a race. Restriction enzymes are trying to break up the DNA. Modification enzymes are to some extent are trying to methylate various areas of DNA and prevent the attachment of the restriction enzymes. It's kind of how they work. Okay, but the restriction enzymes are wonderful from a standpoint of what they've been able to do because they're the foundation of genetic engineering. Really, I think that they are. And then you probably had a bunch of stuff on CRISPR systems, and I'm not really that up on it. Yes? You got that? Is that cell and molecular or genetics? Yeah. If you have any questions, ask her. Above my pay grade. Okay, and then this is one of the questions, the plaque, being able to assay that and, looking to see the effectiveness of it that are there. Animal viruses, this is the big one that's there. Sometimes it'll involve more than one. That's where HIV binding to 2, very specific. That's why we have, when they talk about range, it's not geographic. Range of viruses is species. So influenza has a broad range. Rabies has a broad range. Measles is us. Limited range. And so this is the idea, the difference between naked and enveloped viruses. Naked viruses versus enveloped viruses. And so here, whether or not your entry by endocytosis very comparing by membrane fusion. So you have to have a membrane being enveloped virus to fuse. That's the nugget. They both eventually uncoat. That's there. Then these are all of these steps. And the only reason that's important to understand that the steps that we interfere with antivirals are attachment. So they have entry inhibitors. Again, the uncoating, they were not very effective, these anti-encoding ones. The synthesis ones were very effective and are still used. And what they basically are in the same category. So you're talking at Valtrex, valacyclovir. I believe that's adenine related to certain types of adenine compounds. And what it's doing is it's blocking or incorporating something that would terminate the chain of replication that when it has to incorporate adenine. It's there. So they are nucleoside-based inhibitors. And you have some that are non-nucleoside, and that has to do with things like the integrase proteins or for retrovirals that combat the RNA reverse transcriptase, HIV. And then you have protease inhibitors because a lot of these make those long protein strands, these polyproteins. And what protease does is chops them. If you inhibit that, that's the way it releases. So on the same strand, it makes spike proteins, capsid proteins, and other proteins. But in order for it to assemble, basically you have to chop that up. That's where protease comes from. So they look a little bit at replication strategies. These are with the positive and negative. So you can see that, if it's the double-stranded, single-stranded positive, single-stranded negative, has to make double-stranded positive and negative, then single-stranded, etc. And so there's subtle changes. Again, I don't know how significant that is. This is the big deal, the genetic reassortment. So whether it's influenza or to some extent COVID, which are RNA viruses, those strands of RNA, as they replicate, little portions can move. It's called antigenic shifting. And so there's really two. When it's very subtle, particularly in influenza, it's called antigenic drift. It alters the spike proteins enough that when they make influenza vaccines, that you have to make them on an annual basis. Antigenic shift involves two and this is what sort of a la COVID. So let's say allegedly the Wuhan market, depending on who you read, the Wuhan lab. I'm not, because it was politicized extraordinarily. So whatever your feelings about that, or wherever you fall on the political spectrum, wherever you listen to, you might have a different idea. Long story short, somehow, some way, multiple species that had coronaviruses interact in some way, shape, or form. And portions from different species came together to make what we call a novel, which means new, not seen before virus, that our defenses couldn't cope with. And it viciously attacked. So whether this was genetically engineered or whether this was just happenstance, obviously, would it be fair to say that the world changed? I think so. Go figure. Sorry. Now my sister and brother-in-law won't talk to me unless they have a mask. We'll meet with you, but we're never going to take our masks off. Okay, don't. But my brother-in-law is going to be 80, and I understand that. He's in better shape than I am. He can shoot his age on the golf course. He weighs the same as I met him in 1963, 59 years ago. It's awful. Okay, and then they go through the replication, assembly, release, budding or shedding, where it picks up the spikes on the membrane. Acute persistent means they linger. So if you have untreated hepatitis B or hepatitis C, once you get into that persistent stage, this means you're always releasing the particles. Latent, you go through a stage where you're non-infectious until it's activated. HIV is a slow virus which combines both. The latent period, rather than being completely uninfected, you're gradually producing more and more. And when you reach AIDS, now it has become persistent and you're constantly shedding the particles. At that point, what coincides with that is your immune system has collapsed. And your absolute value of helper T cells has reached a critically low level that you're just not going to be able to survive. By definition, HIV is non-fatal but treatable. AIDS is fatal, which means it shortens your lifespan. So that's really the definitions that are there. These are the viruses, with regard to acute and persistent infection. So when you talk about chronic, whether you're in the AIDS or you have late stage liver hepatitis B or C, those are the folks you have to be very careful of when you interact with in a healthcare environment. The risk of having a needle stick from an HIV positive person getting HIV is about 1 in 500. Yes.
Whenever I was back home, I don't watch much TV, but there's all these commercials you had to mean we could be undetected for the virus. How would that be? Obviously, we don't have a cure for it all, so that would probably be.
There are, to me, they're trying to sell antivirals.
Okay.
I mean, that's you're seeing. We never used to have treatment for HIV, for hepatitis C. None.
Yeah.
And what happened was that they developed some good new treatments. All they had was interferon and some very harsh antivirals. Now there's some better antivirals. So folks with Hep C, and so there's a lot of people who have it undetected. My wife was one of those, my first wife. She probably got that because she had a transfusion back in '81. I'll tell you about this when we get into physiology. So the rest of the class will hear about it. She before 1987, the blood wasn't well screened. She probably got it from that. It wasn't detected till about 25 years later when she had a work-related blood splatter at a nursing home. And all of a sudden, she's Hep C positive. Calls me on the phone in tears. Oh my God, I have hepatitis C. Well, fortunately, she tested positive. She didn't have, you do PCR RNA testing. She didn't have it in her bloodstream. But the reality is, because her health has deteriorated over these last 20 years, unfortunately, and we're still in contact all the time. She has COVID right now. My daughter called me up, Mom's got COVID. So, but the reality is, they were told that, that Hep C could rear its ugly head because your immune system keeps it trying. So that's part of it. Where they, again, herpetic viruses, dorsal root ganglia of sensory nerves, anywhere. Whether trigeminal like this, sacral, if we're talking about, genitourinary herpetic infections. Know this, HPVs, tumorigenic hepatitis B and C, because they affect liver cells, which are so rapidly reproductive. They are that. So this is an important chart. Epstein-Barr. So mostly these are herpetic. I don't know enough about this rare RNA, the HTLV1, but Hep 8, herpes 8 rather, Epstein-Barr are the ones that are significant. The herpetic group, hepatitis B and C, even though they affect, because it has more to do with the liver cells themselves. And then that's all lab. I'm not doing that. Don't know anything about viroids other than they're just RNA short chains and they affected. Prions. Okay. Proteinaceous infectious agents is how they develop the name. All we know, they are misfolded proteins. The most interesting about them is that they consistently cause spongiform encephalopathy. The brain takes on a spongy area from areas of deterioration. It looks a whole lot like Alzheimer's. So we certainly know that about 5% of Alzheimer's are directly related to prion infections. but they consistently are, we think they're transmitted by ingestion. And it's neurologic material. Where it came from mad cow, what they used to do to feed cows is they ground up cows that were for meat, they ground up the remains, called it bone meal, and threw it into things like dog food and feed for the cows. Well, how's Uncle Charlie? Delicious. One person laughed. So, and you can see, this may all be the same disease. So whether it's mad cow, or scabies, or deer and elk, or whatever it is, or exotic ungulate encephalopathy, kuru. Now, kuru is one of them. So cannibals were known to go crazy, and it turned out when they were able to find preserved neurological remains, they had. So basically, they bounce proteins that are misfolded, bounce into other proteins and hurt them. Yeah, go ahead.
So my brother, I took micro in high school, and obviously we took it in college as well. But remember, we did like a deep dive into like prions and everything.
Mm-hmm.
With like chronic wasting disease with like deer. I know that like they're like called like zombie deer or whatever. Like they're just chunks and hunks missing out of them. You know, they're still walking around fine. Is that like would it be inside of all of their cells, or would it be inside brain tissue?
Just brain tissue.
Okay.
Brain tissue. I mean, I don't know enough about it.
Okay.
The only deer I see are where I walk the dog. They're right there.
Gotcha.
That's why we live in the woodlands. Deer everywhere. She still hasn't come over to see the dog or the cats.
Come over.
You're terrible. In the spring when you're out of school.
Okay.
So, and that's the whole nugget there. The other, let me show you this real quick. Help! No, time is.
You got 10 minutes.
Oh, I got 5.
Actually, 5.
She told him.
What? You got 5 minutes.
Yeah. Oh. I'll figure this out. No, I might just I got a message I'm trying to solve the answer to, but I will. Okay, where was I? Okay, here. I want to show you that stuff about shift and drift because I think those are things that you're going to probably see. This was micro. Okay, good. Here you go. So, and this will be true for COVID as well. Okay, so this is what happens is the spikes. So this is the distinction of antigenic shift and drift. There are 2 types of spikes called H and N spikes, stand for hemagglutinin and neuraminidase. That's how we categorize it. So when you hear H1N1, H5N1, H1N3, there's about, as you can see, there's about 18 H subtypes and 11 N subtypes, and these are the ones, and H5 also affects humans. I don't know why they don't have that. And I've done a lot of reading about it. It's very interesting, about the very famous flu of 1918, the so-called Spanish flu. But what happens, the distinction is this idea of drift is minor mutations. That's what's causing some of these how COVID presents differently. It's undoubtedly antigenic shift. Do they have the same markers? I think they have a hemagglutinin, which is typically for attachment. I do not know about the neuraminidase. Okay, and so it changes seasonally. Where this is the notion of how we got these really nasty novel, the COVID-19 came from uncommon. And because in influenza, they have 8 different identical strands of RNA that have mutated. Here, and exactly how it translates to COVID, I am not sure. But effectively, this was how they thought the Spanish flu, which was a bird-based flu, that you probably typically on a farm or like a market, a la Wuhan, you have You see, here you have a duck and a human and a pig. So the farmer have fowl, they have pigs, and all of a sudden everybody gets sick. And you have managed to incorporate, an oddball in from a different species, and you create a multi-species virus. So you have a bird virus for avian flus. You have a big swine flu, which was very, very famous back in '76. They were going to immunize everybody nationally. '76, I was a medical student, and all of a sudden they started the program. President Ford, because Nixon resigned, started the program, and they stopped the program because about a half dozen people, that for some reason they started in Wisconsin or Minnesota, got a thing called Guillain-Barré syndrome, which is not which occurs with any kind of immunization. But they had a cluster of 6 cases, and it's an ascending paralysis. And they immediately stopped it because they thought, first of all, I don't even know why they started it, because they were concerned it was going to be an outbreak of the Spanish flu. That's kind of where that all initially. So they microbiologically, I just thought I'd throw that in for the sake of completion. Now, one other thing I wanted to get to down here at the bottom, the genetic basis you have. And really, to me, this is the big problem we're seeing vis-a-vis microorganisms, particularly bacteria. The fact that they are a living population, we have aggressively treated them with strong antibiotics, and unfortunately, it's chemical warfare. I mean, there's no other way to say it. This is chemical warfare, and what does a species do? It mutates, and it leads to mutations or spontaneous mutations occur that facilitate their survival. Okay, because what's a mutation? Descent with modification. So we have Staph aureus, 95% of Staph aureus was susceptible to penicillin when we first identified it and penicillin was first identified and first utilized around 1941. Okay, at the start of World War II. We have mutated it at least twice since then. So we mutated it once where it was no longer susceptible to basic penicillins. So we ended up with a mutation that required more advanced penicillins like methicillin and ones that are similarly related, because you have types that are active by injection and types that are active orally. And then we've mutated it again. Now in the hospital and community-based, we have agents, we have variations that we call MRSA. And now we're mutating it yet again into something called VRSA, which is vancomycin resistant. Vancomycin was a drug of last resort that was used for gram-positive infections. And that came from other antibiotics that were being used enterically. Vancomycin on something called Enterococcus faecalis. So it's just, and I've seen this, I can't even begin to tell you how we didn't know, and maybe the little nugget I'll give you as we're concluding. About 1990, I'm going to say 94, where PPG Place, for the old, not the Civic Arena, where, that was, where the Penguins are playing. That was a hospital. It was called Central Medical Center, and then it became St. Francis. Acquired it. I was on staff at both of those. That's where I operated. So I walked in the doctor's dressing room, do a surgery, and there was a sign, there was a notice, read this sign at the bottom. Be advised that we will not fill your prescriptions for vancomycin unless, you meet the following criteria. You can document you used other antibiotics. You can document the sensitivity, blah, 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 blah. So basically the pharmacy is saying to the doctors, we are not filling it in this hospital because we're getting too many cases of vancomycin resistance. Of Staph aureus is not responding. Hello? I mean, it's not often that the pharmacy mandates to the doctor. And basically, it's a letter from the head of the pharmacy and the chief of the medical staff, the administration. Okay? You're not using it no more. All right. So, and now we see what that's, and so we really, and there's so many other super bugs being developed. So you can see 60% of Staph aureus strains from hospitalized patients were resistant. And all these people who harbor it, because we harbor staph in our nose. You work in a hospital a couple of times a year, you're harboring a person. that are there. So you have to understand all of these without going into genotype and phenotype, and the nomenclature that's there is the idea of mutational. And the big problem with bacteria is that we mutate it very easily. When you submit them to those chemicals, again, if they undergo mutation, normally the rate is maybe 1 in 10,000 to 1, whatever this is, in a trillion. It increases by a factor of 1,000. So you could mutate 1 in 10 bacteria. And so all of those things. The other test that you should know about, and this is the Ames test. Did you learn about the Ames test?
Yeah.
It's a yes or no answer.
Sounds familiar.
Sounds familiar. Any product that the FDA approves has to undergo the Ames test. They test to see if it will reverse mutate an auxotrophic, a resistant strain, a strain of salmonella that requires histidine. If it mutates it back to non-histidine requiring salmonella, that's such a severe mutation that it fails the Ames test. And the FDA won't approve it. So we use bacteria, you mix the bacteria with some rat liver enzymes because typically you need activation, and they combine whatever chemical or agent or drug they're testing. We'll stop with the Ames test. We'll do the genetics and the bacteria on Friday and hopefully be done with this. Happy days. For those staying, let me catch my breath. Let's see what my son wants from me.